I was watching a demo the other day of a highly advanced robotic arm, the kind of tech that's supposed to revolutionize our factories. It looked sleek, precise, and incredibly expensive. The engineers were showing off how it could identify objects using the latest language-integrated AI. When a delicate porcelain vase was placed in front of it, the system immediately identified it, even reciting a brief history of Ming Dynasty pottery. It sounded brilliant, almost human, but then as the arm reached out to move the vase, it didn't just pick it up, it applied enough pressure to instantly turn the porcelain into a cloud of white dust. The robot didn't look surprised, of course. It just kept reciting its facts. It knew the word for fragile, but it had no concept of what fragility actually felt like. It was a genius that didn't understand gravity or mass. For the last couple of years, we've been living in a state of collective AI fever. Ever since ChatGPT dropped, we've treated these large language models like they're the final destination, the ultimate intelligence. We've watched them write poetry, pass bar exams, and code entire websites in seconds. But there's a growing group of researchers, including AI pioneer Yann LeCun, who are starting to look at these brilliant bots with a sense of quiet skepticism. LeCun even left his top post at Meta to focus on a path that many in the industry are only just beginning to grasp. Because here's the unsettling truth. For all its eloquence, ChatGPT is essentially a blind librarian. It can tell you everything ever written about the ocean, but it doesn't know that water is wet or that a heavy stone sinks while a leaf floats. It predicts the next word based on probability, but it cannot predict the next second of physical reality. This realization is sparking a massive high-stakes pivot in the tech world towards something called world models. It's no longer about teaching AI to talk, it's about teaching it to understand the very laws of physics that govern our existence. If the AI we have now is a storyteller, the AI coming next is a liver, and the transition between the two is about to change everything we thought we knew about the digital future.
Yeah, that analogy of the blind librarian, it's perfect. It just cuts right to the heart of the conflict, you know?
Right.
What we've been so excited about for the last couple of years is really the triumph of pure abstraction. These current AIs, the LLMs, they're amazing when the whole world can just be boiled down to tokens.
Like words or code.
Exactly. Words, code, even static images. They live in this purely statistical world.
So they're just figuring out what word is most likely to come next based on everything they've read?
Precisely.
Yeah.
But the second you try to connect that to the real world, the second you introduce things like friction or inertia or gravity
Or a porcelain vase.
or a porcelain vase, that's when the whole thing just it falls apart. The model's complete detachment from, cause and effect becomes this crippling weakness. And that's really what our deep dive is about today. We're going to look at this huge shift.
First, at the tech itself that's enabling this mastery of physics, some people see this as the only way forward, the only way to get past what they call the great stagnation.
And then we're going to pivot. We'll look at the immediate political and economic fallout, the fights over regulation, the arguments about who gets to control this stuff, and even the way our digital world is sort of decaying under its own weight.
Okay, so let's start with that core problem. We've got this blind librarian. It knows the word fragile is often found near handle with care, so it understands the association.
The linguistic correlation, yeah.
But it has no internal concept, no simulation of what actually happens if you apply too much force to something that's fragile.
And that inability to simulate consequences, that's what makes LLMs by themselves almost completely useless for robotics. Physics just doesn't run on word statistics, It runs on these consistent, predictable, causal laws.
So a robot needs to know what's going to happen.
Instantly. When it has to manipulate a new object, it needs to know what happens if it applies a certain amount of torque or if it nudges something a little bit off-center. And this brings us to what researchers call the Vision Language Action Challenge, or VLA.
VLA, so vision, language, and action all tied together.
Right. These models are supposed to map what they see, the visual input, and what they're told, the language instructions, into a real physical action.
Like, put the blue block on top of the red block.
Exactly. And for years, trying to train these VLA models has been, well, just an exercise in frustration, mostly because the main way we've been trying to do it, imitation learning, it just produces these really flawed systems.
Okay, so imitation learning, IL, that sounds pretty straightforward. You show the robot what to do.
That's the intuitive approach, yeah. You feed it a huge data set of human demonstrations, videos, logs of successful attempts, and you train the robot to just mimic those movements. It's basically supervised learning for robots.
But you said it's flawed. The policies it creates are brittle. What does that mean exactly? Brittle how?
They can't handle anything new at all. If the robot sees a situation that wasn't perfectly represented in its training data,
Like the block is a slightly different color, or it's not in the exact same spot.
precisely, any tiny deviation, it immediately enters what's called an out-of-distribution state. And because all it knows, all it has ever seen, are perfect, successful paths, it has no idea how to generalize. It can't adapt.
So it doesn't just stop.
No, that's the key. The error doesn't just halt the process, it compounds. It gets worse and worse with every subsequent move until you have a catastrophic failure. It only knows the one dance it was taught. It has no idea how to recover if it misses a step.
So that's the fundamental problem with teaching a physical thing using only a history of success. It doesn't know what failure even looks like, let alone how to fix it.
Right. And so if imitation learning is too brittle because it can't handle novelty, the theoretical fix, the gold standard really, is reinforcement learning, RL.
This is where the agent learns on its own through trial and error.
RL is absolutely the theoretical fix. The agent learns by getting, positive rewards for doing the right thing and negative ones for failing. In theory, an RL agent doesn't just learn the one successful path, it learns how to recover from every possible mistake it can make.
But there's a catch.
Oh, there's a massive catch. Applying reinforcement learning to real robots is notoriously sample inefficient.
And sample inefficient means it just takes a ton of tries, right?
A staggering number of tries. We're talking millions of real-world interactions, millions of physical pushes and pulls and lifts and drops. It has to do all of that just to explore all the possible states and learn how to recover from them.
So it's like a person learning to ride a bike, but instead of falling down 10 times, they have to fall down 1,000,000 times.
That's a great way to put it. And for a complex assembly task, 1,000,000 might be an understatement. And that level of interaction is, well, it's just completely impractical in the real world. It's slow, it's expensive, it's dangerous. You could destroy the robot.
It's a lot of porcelain vases.
And a lot of porcelain faces. You just can't afford that many failures in reality. And that inefficiency, that's the huge bottleneck that's been holding back general purpose physical AI.
Okay, so let's recap. We have language models that are brilliant talkers, but are blind to physics. And we have a training method, RL, that could theoretically teach them physics, but it's just prohibitively expensive and slow to run in the real world.
Which leads us directly to the world model solution. This is the big idea. This is the technology that promises to solve that brutal inefficiency problem by essentially decoupling the learning process from the real world.
It's about building a better practice room.
A perfect practice room. The goal of a world model is to completely flip the paradigm. Instead of model-free RL, where you're constantly collecting millions of slow, costly samples from reality,
Right.
you use model-based RL.
Okay, can you break down that distinction for us? Model-based versus model-free.
Sure. So model-free is pure trial and error in the real world. The AI only gets feedback, the reward, at the end of an action.
Yeah.
It doesn't have any internal understanding of the rules of the world.
It just knows that worked or that didn't work.
Exactly. Model-based, on the other hand, means the AI first spends its time building an internal predictive simulation of the environment. It actually learns the underlying generative dynamics.
So it learns the laws of physics.
Yes. It builds its own internal physics engine. It learns gravity, it learns about collisions, it learns how objects interact.
And once it has that,
Once it knows the physics, it can simulate everything. It can try and fail 1,000,000 times, learn 1,000,000 recovery strategies, and optimize its own behavior, all inside this safe, scalable, imaginary world. It can happen almost instantaneously.
So it goes from being a storyteller that just repeats things it's read to a liver that can actually predict the consequences of its actions in a simulated reality.
That's the leap. That's the whole game. This imaginary training ground is what could unlock truly rapid acceleration in robotics.
That's a really elegant concept, but the implementation is always the hard part. So let's talk about a specific framework that's actually doing this. It's called World Model-Based Policy Optimization, or WMPO.
Right. This comes from researchers at the Hong Kong University of Science Technology and ByteDance Seed. And what's important is that WMPO isn't just another theory. It's a principled framework that shows how you can practically build and use this imaginary environment for training. It's a big step up from earlier attempts that really struggled with, the simulation kind of drifting away from reality.
Okay, so what makes WMPO different? I know a lot of AI research focuses on using abstract spaces to save on computing power, but WMPO specifically works in high-fidelity pixel space. Why is that so important? Why does the simulation need to look so real?
This is a really critical design choice, and it's all about maximizing efficiency. A lot of the older model-based RL systems, they take all the visual data and compress it way down into an abstract, latent space, just a simplified mathematical code for what the robot was seeing.
But that sounds efficient. Why not do that?
The problem is that the big foundation models, the VLAs that give the AI its initial understanding of vision and language, they were already pre-trained on a web-scale amount of real images and video.
Right. They learn from the actual internet.
Exactly.
Yeah.
So if you then try to train the robot's policy in some abstract coded world, you're forcing it to do this extra wasteful step. It has to constantly translate those abstract codes back into the real world visual knowledge it already has.
It's like teaching someone to navigate a new city using only a complex blueprint when their brain is already hardwired to understand satellite photos.
That is a perfect analogy. WMPO completely skips that translation step. It capitalizes on the visual knowledge the AI already has. It uses a really high-fidelity, pixel-space video generator built on powerful backbones like OpenSora and parts of SDXL to create a simulated video that looks and feels just like the real world.
So the robot is practicing on a video feed that's indistinguishable from reality.
And that means every bit of knowledge it gained from its web-scale pre-training is immediately useful. There's no mismatch. It dramatically speeds up the learning process.
Okay, so the simulation looks real, but there's still a huge challenge, right? The problem of failure. If you train the world model on these huge data sets of successful robot actions, like the OpenX embodiment dataset, well, then your imagination is incomplete. It only knows how to imagine success.
This brings us to their first big innovation. They call it policy behavior alignment. It's their really elegant solution to that exact problem. The initial world model is an expert at imagining perfect runs. But for a robot to get truly robust, it has to be able to imagine errors. It needs to simulate collisions and messes and all the weird states in between.
So how does it learn to imagine failure?
Through continuous adaptation. It's a feedback loop. The world model is dynamically fine-tuned using the real rollout trajectories collected by the policy itself.
Wait, so as the robot tries the task in the real world,
Even if it fails spectacularly.
that new, messy data from the failure gets fed right back into the world model.
Instantly. This forces the world model to capture the exact kinds of failures that this specific policy tends to create. It ensures the simulated world is a faithful training ground for that policy's own unique weaknesses.
So it's like the AI is generating its own personalized curriculum for getting better. It's teaching the simulation how it specifically breaks the vase so it can practice not doing that.
That's it, exactly. It's an incredibly powerful idea.
But generating video frame by frame auto-aggressively, that seems really unstable. We've all seen generative video that starts to look weird and distorted after just a few seconds. How do they keep the simulation from degrading over, say, hundreds of frames for a complex task?
That was a huge hurdle, and it's their innovation number 2, robust long horizon generation. They tackled this problem of error accumulation and visual decay with a couple of clever methods. First, they use something called noisy frame conditioning.
Noisy frame, so they're intentionally making the input images messy.
They are. During training, instead of feeding the model perfectly clean frames to predict from, they intentionally perturb those frames with a bit of diffusion noise. It's like training with slightly smudged images.
Why on earth would you intentionally degrade your training data?
Because it makes the world model much more robust. By learning from slightly imperfect inputs, it gets way better at handling the small inconsistencies and errors that its own imagination will naturally generate over a long sequence. It learns to not get thrown off by tiny imperfections.
So it could generate hundreds of frames for a full complex task without the quality falling off a cliff.
Without any noticeable degradation. And the second part is frame-level action control. They use mechanisms like addl-n to embed the robot's action signal directly into the visual generation process for each and every frame. This makes sure the action and the visual output are perfectly aligned, which gives it stability over these really long trials.
So they've built this robust, adaptive, high-fidelity imaginary world. The final step is to actually do the training. Since it's all happening in simulation, they need a method that can really take advantage of all that imaginary data.
Exactly. So they can throw out the costly, slow, real-world interactions and replace them with hundreds of thousands of imagined attempts. And for the training itself, they use group relative policy optimization, or GRPO.
Why that specific method?
GRPO is known for being really stable and scalable, especially in situations where the rewards are sparse.
Meaning you just get a simple success or failure at the very end of a long task with nothing in between.
Right. And the huge advantage of doing this in an imaginary world is the scalability advantage. Think about it. You can run trials from the exact same starting position over and over again instantly.
Which you just can't do in the real world. Resetting a physical experiment takes time. You have to recalibrate everything.
It takes a ton of time and often human intervention. In the simulation, it's instantaneous. And that ability to instantly reset and iterate is exactly what you need for the large-scale training GRPO requires. It enables learning cycles that are just orders of magnitude faster than what's possible with physical robots.
Okay, one last piece of this puzzle. How does the AI know if it succeeded or failed in its imagination? If there's no human watching, how is the score kept?
They use a lightweight reward model. They train this little model on a small set of real video clips that a human has labeled as success or failure. Once it's trained, it's incredibly reliable.
Yeah.
The researchers reported an F1 score of over 0.95.
So it's almost perfect at judging the outcome.
Which means the whole WMPO system can automatically tell if an imagined attempt worked or not. And that simple binary reward, just a yes or a no, is crucial. It simplifies the goal so the policy can just focus on one thing, getting the job done.
This all sounds incredible in theory. But the big question is always, does it actually work? Does this fancy simulation training produce a robot that's actually better at living in the physical world?
Well, the numbers from the simulation benchmarks are pretty decisive. They tested it on something called the Imitation benchmark, and WMPO consistently and substantially outperformed the other methods.
What were the baselines it was competing against?
It beat standard online, model-free approaches, like just running GRPO with real-world data, and it also beat standard offline methods. The most common one there is often called DPO, or Deep Policy Optimization.
PPO, can we just quickly clarify what that is?
Sure. DPO is an offline policy optimization method. That means it only learns from a fixed, pre-collected data set. It never interacts with the world. It never generates its own new data.
So it's only learning from history.
Exactly.
Yeah.
Which makes it efficient in one way. It doesn't need a budget for real-world interaction, but it really struggles with those out-of-distribution states, just like the brittle imitation learning policies we talked about.
So how did WMPO stack up against DPO and the others?
It showed really strong data efficiency. Even with a very small budget for collecting real-world data, WMPO's success rate just shoots up, way past the baselines. And what's more important is that its performance scales really well.
Meaning the more real-world data you give it?
The better it gets. When they increased the real rollout budget, say up to about 12,280 trajectories, WMPO improved its average success rate by over 15 percentage points. It's just much, much better at using that messy real-world data to actually improve itself. Because it's not just learning from the data directly, it's using the data to make its internal physics engine better, which then makes the policy better.
The numbers are impressive for sure, but the real proof, the thing that shows it's really mastered the physics, is the qualitative leap. It's the emergent behavior of self-correction. This is what separates the liver from the blind librarian, right?
Absolutely. And there's a perfect anecdote for this. They call it the square task. You have a robot trying to insert a square block into a really tight slot on a peg. The clearance is just a couple of millimeters.
So it's a high precision task.
Very. Now, when the robot that was only trained on perfect human demonstrations, the base policy tries this, and it misaligns the block and hits the peg. What do you think it does?
It just keeps pushing, I guess.
Exactly. It just pushes harder. It has no recovery strategy. It just keeps pressing against the obstacle because nothing in its training data ever showed a collision and what to do about it. It just gets stuck. It's brittle.
Okay, so what does the WMPO trained policy do?
This is the amazing part. The WMPO policy, because it has practiced millions of failures and recovery attempts in its imagination, it shows genuine self-correction. When it collides with the peg, it autonomously executes this complex, multi-step recovery plan.
What does that look like?
It lifts the square up and away from the obstacle, it slightly rotates and realigns its gripper, and then it goes in for a second attempt and successfully inserts the block.
Wow, and that recovery maneuver, that wasn't in the original human data.
Not at all. It's a completely learned emergent skill. It figured out how to fix its own mistake because it had simulated the causal dynamics of that collision and understood the counterforces needed to get unstuck.
That's the core of physical intelligence, isn't it? Diagnosing a physical problem and then devising a physical solution.
It is. And that capability doesn't just make the policy more robust, it actually makes it more efficient.
How so?
When they analyzed the successful runs, the WMPO policies were consistently faster and smoother. The successful trajectories were measurably shorter than the ones from the baseline policies.
Because it's not wasting time getting stuck or fumbling around.
Exactly. The optimization process in that perfect simulation actively punishes any kind of stalling or inefficient behavior. The model finds the most direct, elegant path to success because it's working from a clear internal model of cause and effect.
And that understanding of physics should generalize, right? If it gets gravity and friction, it shouldn't get thrown off by, say, a different color tablecloth.
That's the critical test. And they did it. They tested the policies against a bunch of novel disruption scenarios. They changed the object's starting position. They changed the background color of the table. They even changed the texture of the parts being assembled.
And
the WMPO policy held up. Its reliability stayed high across all these visual shifts, which confirms that it was learning the generalizable manipulation skills, the underlying physics, and not just memorizing surface-level visual cues.
And how did the other one, the history-based DPO policy, do?
DPO's performance fell off a cliff, especially when they changed the background or the texture. That just confirms that it was relying on the exact visual context from its fixed dataset. When it saw a slightly different texture, it got confused because it had no causal understanding of the task. WMPO, on the other hand, had practiced the physics of insertion 1,000,000 times, so it didn't care what color the table was.
Of course, the ultimate test is always moving from the simulation to the real messy world.
And they did that validation. They put it on a real robot, the Cobot Mobile Aloha platform, and gave it that same difficult square insertion task, this time with a tiny 5mm clearance.
And the results?
The results were clear. The base policy succeeded 53% of the time. The DPO baseline got to 60%. But the WMPO policy achieved a 70% success rate on the physical robot.
That's a significant improvement.
It is. And what's more, the framework is built for lifelong learning. The robot is always collecting new data from its attempts, right? So you can just keep feeding that new real-world data back into the world model to refine it further and then re-optimize the policy and imagination. It creates this loop of continuous, stable improvement over time.
So the robot is essentially generating its own expert data to train itself. That's how you scale this without needing armies of humans supervising every step.
That's the path to truly autonomous physical agents.
Okay, so on one hand, we have this incredible accelerating mastery of technology. We're on a path to teaching AI the laws of physics, training it safely in its own imagination, and moving towards what feels like superhuman capability. But the moment that power starts to scale, we run head-on into these massive political questions about control.
Right. If we can build an agent that truly understands and can manipulate the physical world, how in the world do we regulate that?
That tension is exactly what fueled the huge regulatory debate we saw over the last couple of years. The speed at which AI capabilities were growing, I mean, especially the realization that these models were gaining these emergent, unpredictable skills, it set off alarm bells for a lot of experts.
A very wide range of experts. You had the godfathers of AI themselves, people like Jeffrey Hinton and Yoshua Bengio, signing these statements saying that mitigating the risk of extinction from AI should be a global priority, right up there with pandemics and nuclear war.
And that collective anxiety, that fear of existential risk, led directly to California's attempt at regulation. The Safe and Secure Innovation for Frontier Artificial Intelligence Models Act, better known as SB 1047.
Senator Scott Wiener's bill was a direct response to that frontier risk. It was an attempt to create a safety and security framework for the biggest, most powerful AI models being built.
So how did the bill actually define a frontier AI? What was the threshold for regulation?
This is where things got really technical and very controversial. The bill set a very specific computational threshold. It was designed to only target the absolute giants in the industry. It would only apply to models that cost more than $100 million to train and required more than 10 LOPS of compute power.
10 FLOPS. That is a number that is almost impossible to wrap your head around. What does that even mean in real terms?
To give you some kind of scale, the world's most powerful public supercomputers, the ones we use for huge climate models or nuclear simulations, they operate at what's called the exascale. That's around 1018 FLOPS.
Okay, so $10 is many, many orders of magnitude more powerful than that.
We're talking about a truly astronomical amount of computation. By setting the bar that high, the bill was effectively limiting its scope to only the handful of massive tech companies that could even dream of building a model that big. It also said that if one of these covered models was later fine-tuned, and that fine-tuning cost more than $10 million, that new model would also fall under the rules.
And the goal was to prevent the absolute worst-case scenarios, What were the specific catastrophic risks the bill was trying to stop?
It laid out 4 categories of what it called critical harms. And these weren't about things like bias or discrimination. They were about global security threats. First was the creation or use of CBRN weapons. That's chemical, biological, radiological, or nuclear.
The fear that an AI could help someone create a new virus or something?
Right. Second was mass casualty cyber attacks on critical infrastructure, power grids, financial systems, or any cyber attack causing more than $500 million in damage. Third was facilitating mass casualty autonomous crimes. And then a fourth catch-all for other harms of similar severity.
These are genuinely terrifying possibilities. So what would a developer have to do to comply? What were the mechanisms for regulation?
The requirements were really stringent. They would have had to create extensive safety and security protocols before they even started training the model. And before deploying it, they would have to submit a statement saying they'd taken reasonable care to prevent these harms. This also included mandatory annual third-party audits starting in 2026.
And then there was the most talked about requirement, the so-called kill switch.
Yes. The bill mandated safeguards that included a functional kill switch or circuit breaker, something that could immediately and permanently disable the model if it started exhibiting dangerous rogue behavior or was being used by a bad actor.
Which sparked a whole debate on its own about whether a true kill switch is even technologically possible for a distributed, self-improving AI.
A huge debate.
So the bill made it through the California legislature, but then Governor Newsom vetoed it. Why would he reject a bill that was aimed at preventing nuclear and biological disasters?
He vetoed it in September of 2023, and his reasoning was that he had serious concerns about the entire framework. His core argument was that by focusing only on the biggest, most expensive models, defined just by their computational size, the bill created a false sense of security.
You mean focusing on the size of the AI was the wrong way to measure its risk?
That was his point, exactly. He argued that the framework completely failed to consider the context of where the AI was being deployed. For instance, you could have a much smaller, cheaper, more specialized AI model. But if you use it to automate drone targeting or to control a power grid, it could be far more dangerous right now than a giant language model that's just writing marketing copy.
So he felt it was regulating the wrong thing. It was regulating the potential power instead of the actual application.
Right. He argued that these strict standards were being applied indiscriminately. They might stifle innovation on large general-purpose models while completely missing smaller, more specialized, but equally dangerous AIs that just didn't hit that massive $100 million and 10 FTLOPS threshold.
That really captures the central tension, doesn't it? Do you regulate the raw technology itself, or do you regulate how it's used?
And Newsom clearly came down on the side of a more flexible, application-based approach to safety. He said he'd rather work with research institutions to advance AI responsibly without these rigid compute-based rules.
The moment that computational threshold was announced, though, the debate just exploded. It became this ferocious fight over the future shape of the entire AI industry. Let's start with the accusations of regulatory capture.
That was the immediate and sharpest criticism, especially from the open source community and from venture capitalists. They argued that setting that regulatory bar so incredibly high, the 10 FTLOPS, the $100 million, was basically an act of regulatory capture, whether that was the intent or not.
How would that work? How would it lead to capture?
Well, by creating these massive compliance burdens, the mandatory audits, the internal safety teams, all the pre-deployment protocols, you're creating a system that only the biggest incumbent companies can afford.
Only Google, Microsoft, Meta.
The ones who can easily absorb those costs. It effectively creates a moat around them. The smaller startups, the ones who are usually the engine of innovation, they just wouldn't have the capital to comply. So it gives the incumbents a huge market advantage and consolidates power in the hands of the very few companies that already control the most computing power.
So the safety framework becomes an expensive barrier to entry.
That was the argument. And this whole thing just ignited this intense, very public war over the future of open source AI. You had major figures from tech and law taking completely opposite positions.
This was the heart of the conflict.
It really was. On one side, you had someone like Yann LeCun, Meta's chief AI scientist. He flat out warned the bill would kill open source AI models. Period.
Why? What was his reasoning?
The threat of legal liability. His fear was if a company like Meta releases a powerful model for free and then some bad actor down the line uses it to cause one of those catastrophic harms in the bill, the original developer Meta would be exposed to these massive lawsuits and fines.
And faced with that risk, Companies would just decide not to release their models openly.
They can close source. They argued that making a developer liable for how a third party misuses a free open tool was a legal nightmare that would just suffocate the entire open source AI movement.
But then you have the counter-argument from people like Lawrence Lessig, the co-founder of Creative Commons. He said the exact opposite. He said the bill would make open source safer and therefore more popular.
Lessig's logic was that SB 1047 wasn't about restricting open source, it was about making the source itself safer. He argued that if you force the foundational model developers to build in robust, third-party audited safeguards from the very beginning,
then everyone who builds on top of that open source model inherits that safety.
Exactly. The risk of harm would be lower, and therefore the liability risk would be lower for everyone downstream. It would actually make releasing powerful models more palatable, not less.
And this huge ideological divide was just perfectly reflected in the lists of supporters and opponents. It was a really diverse cast of characters.
You had powerful people on both sides. Supporting the bill, you had the figures focused on existential risk, Hinton, Bengio, Elon Musk. On the other side, opposing it, you had forces focused on, acceleration and open access. Andrew Ng, Fei-Fei Li, major VCs like Andreessen Horowitz and Y Combinator, even members of Congress who were worried this California law would kneecap American innovation.
It wasn't a simple political divide. It was this fundamental disagreement on what the biggest immediate risk is. Is it stagnation or is it catastrophe?
And what's so fascinating is how public opinion on this was completely malleable. It all depended on how you framed the question in the polls.
Right.
Polling that was sponsored by the safety advocates, it showed huge support, like 77% when you framed the question around requiring companies to test AI to prevent things like biological weapons or shutting down the power grid. Frame it as public protection, and people are all for it.
But when the opposition framed it differently?
Support just collapsed. The opposition's polling showed 46% opposition when you framed it around creating new state bureaucracies, imposing huge fines on startups, killing jobs, and forcing companies to leave the state. It just shows how caught the public is between this very real fear of AI risk and the much more immediate economic fear of killing innovation and jobs.
This has been a really deep dive into the absolute cutting edge of technology, the AI learning physics, the huge political fights to control it. But let's shift gears a bit. Let's talk about a different, but maybe related kind of failure, the slow decay of the internet itself.
Yeah, this is a transition from the world of, rapid acceleration and frontier risk to the world of economic reality and just mundane decay.
Yeah.
While some companies are building these incredible world models with 10 FLOPS of compute, other older platforms are just collapsing under their own weight. And this decline is perfectly captured by a concept called enshittification.
It is a memorable term coined by Cory Doctorow. How does this cycle actually work for these big digital platforms?
It describes this almost inevitable life cycle. A platform starts out as this user-friendly darling. It's sleek, it's fast, often ad-free, and it offers some amazing utility to get a ton of users on board fast.
They burn through venture capital to get big.
Exactly. But once they have that captive audience, once they've achieved network effects, where the platform is only useful because everyone else is on it, the pivot happens. The focus shifts away from the users who built the platform and toward the business partners, the advertisers, the investors.
So profit starts to matter more than the user experience.
Way more. And that means they start loading the site with intrusive ads, they make user hostile changes, they degrade the core thing that made the site useful in the first place, all to squeeze every last drop of value out of the users they've trapped. And eventually the most valuable users leave, and the platform just fades into irrelevance. The whole cycle is driven by the fact that that first useful stage was never actually economically sustainable.
And the absolute poster child for this recently has to be the big shakeup at Imgur in 2023.
Oh, textbook case. Imgur's decision to ban all NSFW content and, even more catastrophically, to delete every image not tied to a registered user account. That is a perfect example of enshittification. Imgur started as the internet's go-to place for free, easy image hosting for sites like Reddit. But it finally hit that financial point where its core utility was just a massive money pit.
We usually think of these content bans as being about morality or company values, but what was the real brutal reason they deleted all that historical content?
It was almost purely economics and liability. The model of offering unlimited free, high bandwidth image hosting, which was Imgur's whole reason for being, it was just not profitable. NSFW content in particular is a net drain. It uses a ton of bandwidth, but generates almost no ad revenue because big brands don't want to be anywhere near it.
And then there's the risk.
Massive, expensive, unavoidable moderation risks. You have to constantly police for child abuse material. You have the growing fear of AI-generated deepfakes, revenge porn, liability. Plus the constant threat of getting cut off by payment processors like PayPal or Visa if your moderation isn't seen as good enough. To manage that at scale for a free service is just prohibitively expensive. Imgur realized its original mission was a financial trap.
But deleting the image is not tied to an account? That's the real blow to the internet's history. That was the platform's original great strength.
It is the cardinal sin for an image host. You do not kill the old links. For more than a decade, Imgur's strength was that you could upload an image without an account and hot link it anywhere. By deleting all of those, they destroyed their own foundational utility for a huge ecosystem of forums, wikis, Q&A sites that all relied on it.
So it created another photo bucket situation.
A massive new photo bucket situation. We are literally watching a huge digital graveyard form in real time. All of those deleted images are breaking countless links that are embedded deep inside a decade of internet history. Old forum threads, troubleshooting guides on Stack Overflow.
So much visual context is just gone.
Just gone. Years of collective knowledge just erased. It really shows how profoundly unsustainable so much of our digital infrastructure is. We built the internet's memory on business models that were never going to work long term.
And when you look for alternatives, the problem's right there.
It's obvious. The small donation-footed hosts can't handle the scale. And the paid enterprise services don't have the ease of use or mass adoption to serve that public utility function. It just confirms that unlimited free image hotlinking is not a viable business model. This cycle of utility, growth, decay, and enshittification. It's just a fundamental pattern of the digital economy.
So this deep dive has really taken us from the absolute peak of technological aspiration down to the grimiest economic realities. On one side, you have WMPO driving this incredible acceleration of physical AI, promising autonomous agents that can actually live in the world and learn physics safely in their own imagination.
And that acceleration has happened at the exact same moment that we're seeing these fierce regulatory battles like over SB 2047, where we're fighting over how to control that very power. The debate over a kill switch and a 10 FLOPS threshold immediately becomes a fight about market control and open source liability.
And all the while, the very foundation of our digital world, our shared memory, the image hosts, is fracturing and decaying because of basic financial reality, perfectly shown by what happened to Imgur.
There's this profound dissonance, isn't there? We are simultaneously inventing these astonishingly powerful autonomous minds that are mastering physical reality, while the digital infrastructure we use to communicate, remember, is literally crumbling under its own unsustainable economic model. The technology is racing towards autonomy, but the governance and the platforms that house it are just decaying.
The central technological question of our time, then, might not be which AI can write the best code, or even which one can handle a porcelain vase most gently. It might be whether our relentless drive for perpetual technological acceleration will ultimately undermine the stable, predictable reality, both physical and digital, that humanity relies on.